questions, we take it. All right. And yeah, of course, you're also free to interrupt me. I'm looking at the chat window as well. So you please type your message from there. All right. So I hope that you're having a good time learning. At times, for some of you, it will be very challenging. I also see some of the names here. You have already, some of them have actually done it last time also. So it's nice that you're reviewing these things. And yeah, so we are there always to help. Let us know. We're happy to engage in technical questions, all of us, almost always. So tomorrow we'll also have a review session wherein all of us will be present and we can take some questions if required. So with that, yeah, so the topic for today, this session, is dry etching, right? So you have taken, I think Professor Prem was giving a talk, I suppose this morning or last evening. When was that? Professor Prempal gave a talk, right? Yes, you can.
Yes, sir.
Yeah, was it this morning? Yeah.
No, sir. Yesterday he gave a talk.
Okay, fine, good. So he must have shown you some structures like this. So what you are seeing on this slide is some images of silicon. Okay. So after different etch times, you have some shape which is etched into silicon, right? So is this etch isotropic or anisotropic?
Anisotropic.
Anisotropic, right? So yeah, we are able to fabricate some features like this, and they're quite anisotropic. So is it? Why do we need what is called as dry etching? And what is dry etching? Yeah, any ideas?
So the use of gas phase etchants instead of liquid etchants.
Good, Abhinam. So why do we need gas phase etchants?
So I think the gas phase
The
etchants
diffusion is better.
are lesser invasive.
Lesser invasive, but do you think we need more invasive species for etching or less invasive species for etching? To my knowledge, to my, I mean, as a first thought, I would assume that I want more invasive species for etching so that I can always etch faster. What is very nice, Pawan? Good. So isotropic etching means, I'm sorry, I don't have my tablet today, so I have to use this, which I'm not very good at. But let's assume, let's talk about it with the laser pointer. So if you have, let's say, some structure to be etched like this, how does the etch proceed? Does it go uniformly in all directions? If it goes uniformly in all directions, it is isotropic. If it is not uniform in all directions, it's anisotropic. For example, you created a window like this, right? Some window was created with lithography, and then you expose, you protect all these regions around the square with a photoresist, and you dump this piece of silicon into etching solution, maybe TMAH or KOH or whatever, right? In this case, it's not mentioned here, but yeah, one of these etchants. And then you'll slowly start, wherever it is exposed, it will start getting removed, right? And you see that as you etch for longer and longer time, you're actually going deeper and deeper into the substrate. And that is what you're seeing here, okay? So isotropic etching is essentially something that etches uniformly in all directions. Anisotropic is, it preferentially etches in one direction and not in other directions, okay? So for example, if it was isotropic etching, you will not have this sharply defined pyramidal kind of structure. This is, by the way, a pit, not a pyramid, right? It is actually etching into the substrate. It can sometimes be confusing, but you just have to look at it in the right way, okay? You're essentially making a hole into the substrate, which looks like almost like a pyramid, inverted, you're digging a hole, pyramidal hole. So this is anisotropic. So now, if you have if you have this isotropic etching and you're able to control these features very well, why do we need anisotropic etching and why do we need dry etching? That is a question. And the dry etching process, as somebody just mentioned, that you use gaseous phase. Okay, we'll come to the details of what it is and so on. All right. So now, to understand it a little bit more, this is what is presumably happening, right? You have a substrate which is silicon. You have a photoresist. There is, you expose a photoresist and then develop the photoresist. You have a kind of a hole in the photoresist here. And now you put it in a etchant solution and etch will go underneath. And actually, if it's an isotropic etching process, all the directions will be uniformly etched. So you should get something like this after mask removal, right? If you remove this photo mask, you'll end up with something like this. And clearly, what you're seeing in this picture is not like that. There is some sharp edge there, right? So it is not really isotropically etching. That's why I said it is anisotropic etching. That was the answer. Is that clear? Okay, we'll come there. Yeah. So now, if you have such a structure, one moment, just one second. Yeah. If you have such a structure, can we do this structure shown below, right? If you have this wet etching process, the question I'm asking is, can we fabricate something like this, which is shown in the image below, wherein you have silicon again, but then you're actually making holes or trenches in silicon, okay? And this is pretty high aspect ratio. So if you look at the depth of this, I mean, I can't clearly show you this, but this is taken from Oxford, which is actually a etching machine that we have here. So I've taken it from their slides. So essentially what you see is about 150 microns of etch depth, okay? And the sidewalls are extremely smooth. And you have almost nearly vertical sidewall, less than, whatever, yeah, you basically have almost 90 degrees, right? Nearly there. And etch rate is, you have to etch for about 2 microns per minute. So if you want 150 microns, you'll have to etch at least for 75 minutes or so, okay? So you etch for a long time and you get something like this. Is it possible to get with an isotropic etch process, right? As some of you are already saying that it is not possible, right? You see the problem with that, all of you? So if it was an isotropic process, the etchant will go here and then it will start etching underneath and then everything will get dissolved and you will never be able to make high aspect ratio structures. These kind of structures are called high aspect ratio because you have the height, which is very large, and the width, the gap is small. So let's say if I define this as my y and this is my x, y by x is very large. Okay, in an isotropic process, y by x will be almost 1. So the etch rate in the lateral direction and etch rate in the vertical direction are almost equal in an isotropic process. In an anisotropic process, that is not the case. All right. So when you talk of any etch processes, we have certain figures of merit. So we have to compare with those things. When you are, if you understand them, you will be able to compare various etch processes. Okay. So what exactly is happening in the etch process? So you have a substrate, you have a film, and then you have some etchant species. There are some reaction species here, reactants, and they are coming in near the surface. They are chemically reacting with the surface, and then there is some byproduct which is formed, and the byproduct has to go out. So you have the incoming reactants, a reaction happening, and then the outgoing products. Okay. So this is the basic process. Even what exactly is these chemicals and all will change. We will talk about that a little bit more. Okay. Now, when you have wet etching process, wherein these reactants and then the products are all liquid phase, there is a problem. Any guesses? What is the problem?
Release of H2.
Sorry, who spoke? Release of? Prem. What is the problem?
The release of gaseous components like H2.
Well, gases is better. They'll go out faster, no? The main thing is think of it like, the liquid that is there.
That's an accumulation of the byproduct on top of the film because
yes,
diffusion
The
rate is very
byproduct
slow
size
in
also.
right. So basically, yes. So basically you have this very close to the surface, some layer, boundary layer, wherein how do you force these reactants to come in and then byproducts to go? If you simply put it in a crucible, it doesn't happen, no? There'll be, there'll be that at the interface, initially there'll be a very fast etch rate, but then unless these byproducts go out and get mixed up in the solution, the new reactants cannot come in. Think of it like, let's say you put some kind of a colored, mass transport. That's good. I mean, Ranadhir is a MSME student, so he knows it. Right? Ranadhir, no marks for this. All right. So, you have various unit processes, which is etch rate, right? The rate at which your reaction is happening. Is it uniform or not? That is going to be important. Okay. Again, in a wet etching process, that can be limited. For example, because your transport is limited, the amount, you cannot probably get these reactants in time or uniformly across all the surfaces, especially if you have a surface which is very deep here. If you want to get H reactant into that surface, it's going to be very challenging, right? For all these reasons, wet etching has some issues. And of course, etch rate uniformity, and then I don't know why, etch uniformity, etch rate uniformity, more or less both are similar. I don't know why I've written it twice. Anisotropy and selectivity. Anisotropy, I already discussed. Selectivity is essentially, if you have a mask like this and you have a substrate like this, you want the substrate to get etched and not the mask, correct? If your mask is getting etched, it's not good for you. You want to protect some areas only under the area, wherever the area is open, that's where you want the reaction to happen. You don't want the reaction to happen, let's say, somewhere here under the dark gray, right? So for that, you have to have a mask which is sufficient to prevent etching, okay? Think of it like, I don't know, anybody fabricated PCBs?
Fabricated, yes.
Yeah, copper clad FR4 substrates are there, no? So you want to define some circuits on that. You basically can put some kind of a Kapton tape or something and then cut the tape and then dump it into a ferric chloride solution, right? And you will dissolve the copper. Essentially, that's a wet etching process. And the mask there is basically your Kapton tape. So Kapton is protecting, that's why, and you want the etch rate to be selective. If suppose you have some other etch process wherein the copper and the Kapton tape get uniformly removed, then you don't have a high selectivity process, right? So you need extremely high selectivity process, okay? All right. So with that in mind, the basic dry etching reaction is for silicon. I mean, because silicon is one of the most important materials that you have to etch. For silicon, this is how the etch reaction looks like. So you have some solid, which is silicon, right? Silicon wafer. You have fluorine gases, which are basically, we'll figure out why the fluorine gas is coming in. And then when these react, and then you get a silicon fluoride, which is a gas. Okay. So with this, you are able to remove solid with just a gas being present, right? So that's a basic dry etching process. Can you say how anisotropy affects again? Anisotropy in the context of Anand?
Sir, here, what are the factors determining dry etching? You have written 0.4 anisotropy.
Right. I'll come there.
Okay.
I'll come. Why dry etching is anisotropic, right? I'll come there. We have to understand a bit. Okay. Yeah, you're right. So for example, if I give you a silicon wafer and I'll give you lots of fluorine gas, right? I'll put the silicon wafer in a kind of a chamber and I'll connect it to a fluorine gas and I just pump fluorine into it. Will it be isotropic or anisotropic? Anand. Yeah. Isotropic, no? Absolutely, correct. Just because you have a gaseous phase, why should it be anisotropic? Any ideas? Yeah, I don't know. I hope not, but some of you might be smoking cigarettes. You are isotropically etching your lungs, maybe. Right? How do you make it anisotropic?
Control the reaction rate with some energy, like
how do I control the reaction rate with energy?
Gas.
Sorry?
By reducing the randomness of the gas, like by making
Very nice. How do I reduce the randomness in the gas?
Focusing it like a more.
Adya, control the speed of the flow of the gas. But is the problem the speed of flow of gas? For example, Adya, I'll take a chamber, I'll pump it with fluorine gas, and then the way you measure the flow of gas is by what is called as SCCM, standard cubic centimeters per minute. Okay, that's one of the usual measures that we have. So I'll basically flow a lot of gas in and I'll pump out a lot of gas. So I can basically control the speed of flow of gas, but that doesn't really solve the problem. Okay. So flow of gas is not enough. How can we reduce the randomness? Oh, very nice. Our BTech students are waking up. Are they equally? Okay, good. Anyway. Yeah.
Sir,
Yes.
could it be like targeting the gas only on a particular specific area?
How do we do that? I mean, for that you have a mask, right? That's all right. You have a mask, you will be able to do that. But how do we, the question was, if you have dry etching, my argument is, you think of a chamber with silicon present and you pump pressurize with some kind of a gas, you're going to have isotropic etching. Why should it be anisotropic? Just because it's dry, right?
So we could use an electric field to direct, to accelerate the ions vertically.
Wait, that we will go there, okay? What is a bombarding gas? Ohm. I believe okay, yeah. Ohm, you want to speak up? Yeah.
Yes, like he said, with using electric field, if we just.
But, okay, think of it like this, Ohm. I have two metal plates. I apply voltage. Will I make the gas directional? It's a very important point. Very good. Ohm.
Yes.
Yeah. If I just place it two metal plates and I apply voltage, there will be an electric field. Will that make the gas anisotropic? It is still randomly scattering, right? I mean, you have collisions, random collisions. It doesn't make it anisotropic.
Sir, if
Yes, very good. So we are getting there, right? So you understand, it's not just gas. It has to be some kind of an ionized gas. That is number one. It doesn't just help if you have just a uniform gas. You have to create ionized gas. When you have ions, then actually you have, oh, very nice. Parashuraman, you were there last time. So no credit for you as
Yes,
well.
sir.
See, no credit for
okay.
you. Yeah, all right. Well, it's okay. Okay, all right. So, yeah, you need an ionized gas, right? How do I create an ionized gas? Lohit, you want to say something? Cooling. All right. Anyway, I think at this rate I will not finish. So let me go quicker. But yeah, I'll come to it in a moment. Let's because we went somewhere else. I want to go here. Okay. So it is not enough to just have replace liquids with gases. You need to do something more. What do we need to do more? We have to create what is called as a plasma. Oh my God. Ashutosh, alpha particles, my nuclear physics is, I think I've forgotten after 2005, I've never touched nuclear physics. So yeah, you don't want to go into radioactive decay and so on. Okay. Yeah. It actually causes a lot more problems. As I'm sure Kaushik would have told you, there's a lot of other problems. Anyway, coming back here, it's not enough to have liquids. You can't simply have gases. You need to create a plasma. Okay. A plasma is also sometimes referred to as a fourth state of matter. Just like solid, liquid, gas, we also have plasma. And what it essentially means is you ionize ions. You ionize molecules or atoms. And then you have these ions and then the free electrons. Okay. And they can move about. And these are typically very highly energetic. So the ions have a large kinetic energy and they end up being much more reactive. So there are things like free radicals and so on, which are much more reactive than regular gases. Okay. So what could happen is something like this, right? You have two electrodes, a simple capacitor, let's say. I'll put a DC voltage. Okay. And then there's a large electric field. So what will happen is your electron can be ripped apart from the atom. Okay. Let's say these are fluorine atoms. Somehow I got them there. Okay. Then you're ripping apart the electron from the atom. And then that, because you have an ionized species, electron will, is very, very light. It will quickly travel to the electrode. Ion will travel a little bit more slowly because it is heavier. And then it goes and collides with one more atom. It causes one more ionization event, another ionization event, and so on. So essentially, you are creating a cascade of ionization events, and then you are creating a plasma. Okay? Does that make sense? Something like this happens in your arc lamps, in your lightning as well, right? When you see the glow, lightning glow, that's essentially a plasma being created. You have a large potential difference between these two places, and then there's an ion. There's this electric field, and because of that, you start creating these ions, and then they will accelerate, release lots of light. That's good. That's how you get the lightning, right? That's a plasma, and it's also in the interstellar space, a lot of stars exploding and things like that you have, right? In those also you have a lot of this plasma in the universe. Now, there is a problem with this scheme that I have shown here. Anybody can guess what that is? Reactive ion etching. Vaibhav. We will go there. We will talk about that. Anybody wants to guess what is the problem with this scheme that I'm describing here? Oh, Lohit, very nice. Why low pressure?
The less number of molecules to collide.
Sir, we just have
No.
to direct the plasma, no, sir. That is our main problem.
The mean path.
Yeah, mean free path is how much? Mean free path will reduce or increase with pressure?
It will increase, sir.
Mean free path will increase with increasing pressure.
No, sir, decrease.
Decrease.
Very
sir,
good,
it'll
very
decrease.
good, very good, right? So if your pressure is less, your distance between collisions or the time between collisions reduces, increases, sorry. If the pressure is less, the mean free path increases. And so your atoms can go longer distance before encountering another collision event. Why is that useful? 1 second, 1 moment. I'm sorry, guys. I have to take this. 1 second. Okay. Okay, fine. He stopped. All right. Tell me.
It
If the
evenly
mean free
distributes.
path is less, then there'll be more chance of recombination to become atoms.
Well, I would not call it recombination, but essentially you're losing energy. See, it has to gain kinetic energy as it travels through the gas to cause one more event, ionization event. But if it doesn't travel sufficient distance, it does not gain sufficient kinetic energy, right? So it does, and that energy, whatever it is gaining, it is losing to other atoms. So essentially it is, in some sense, heating up the entire gas. The temperature of the gas increases, but not really ionization happens if you have high pressure. Make sense? So if you have broken a bulb, you will see that pop sound. Why? Because it's under pressure. Arc lamps are under low pressure because otherwise you will not have ionization. Okay. All right. It's easier to cause ionization at low pressure. Any other problems? It evenly deposits. What deposits? I don't want deposition to happen. I want etching, my friend.
Sir, maybe, sir, the proper direction of the plasma may not be taken place.
Yes,
We
correct.
just-
Very good. Very good. That's one of the advantages of, if you want the plasma to be more directional, you want to have low pressure. Correct. If you have high pressure, you will not get directionality. So if I go back and say that if I want to etch this kind of a structure, okay, even if I get the ions somehow, if I have high pressure ions, my ions will collide with each other and start etching underneath the mask also, right? Right? You see that. Isotropic, it becomes more isotropic if you have high pressure. Nishant, okay. Okay. Don't open your mouth so wide. All right. Okay. Is it not true? Yeah.
Sir,
Does it become isotropic or not? High pressure, more isotropic. Low pressure, more anisotropic. Agreed? Everybody? Good. All right. Let's leave this and come back here. Okay. Now, there's a problem with this still. You have not addressed one major problem.
Sir, we should probably use alternating current source here.
Absolutely. I'm sorry, Rahman. What's your name? I'm sorry, I'm not seeing your full name. Saidur.
Yes, yes.
Saidur Rahman. Yeah. Alternating source. Why alternating source?
Because
Not
then,
DC.
since we are making plasma here, ions will be there. They will get accumulated somewhere
Very good.
on silicon.
Absolutely right. Very good. So
Yes.
essentially, even if your ions, let's say, move towards this direction, no, electrons will move this direction, ions will go opposite direction. This is positive, right? Electrons will be traveling towards this direction. Okay, even if you have that, they'll start accumulating on that. And let's say ions will accumulate on this side, right? Positive ions. And then it will prevent further ions to come in. So automatically the charge accumulation on the electrodes will actually prevent further ionization. It will limit the ionization. So instead, you need to have an alternating source, right? So this is what we call as reactive ion etching. Okay, as simple as what we described so far. You have electrodes. If you guys come here, we'll actually open up one of these chambers and show you the electrodes. And then this Oxford machine, we have this Oxford machine that I showed you in the initial one. Okay, so you have this two plates, You put one of them as ground, and then you put an RF input. The RF input, essentially what it does is, you think of, let's say, an atom, right? You're applying a high voltage, it rips apart the electron, and then the ions will go in one direction. But because ions are heavy, they don't travel very long distance. Electrons will fly into the electrode and then reverse. So ions will essentially go back and forth in somewhere in the middle of the chamber, and they get, you just basically have more and more ionization happening. Okay, so that's what is being shown here. You essentially create this plasma in between the electrodes. All right. Now, this plasma is not a simple plasma. Typically, you go to what we call as, this one of the units of measuring it is millitorrs. 760 torr is atmosphere, right? So millitorr, very, very high vacuum, medium vacuum, let's say, not high vacuum, medium vacuum. You have 20 millitorr, or this is roughly 2 pascals or something like that, 2 plus pascals. So if you have this, you have roughly about 10 power 15 per centimeter cube neutral species. Okay, the reactive species are very, very less. 10 power 12 to 10 power 13, less than 1% of the gas is that. The ions and electrons are even smaller, 0.01%. Right? So when we say plasma, it is not that all atoms are ionized. No, it doesn't happen that way. You don't have to have that much of extreme ionization. Okay, it's probably energetically even difficult to have that, because once you also have the recombination, as somebody was talking, right? The electron again being captured by the atom also can happen. Okay, so you don't have this. Typical plasma contains less than 1% of reactive species and less than 0.01% of ions and electrons and so on. Okay, so if you have such a scenario, you will see something like this. This is a chamber, a plasma etching chamber, reactive ion etching chamber. This entire thing is under vacuum. You have 2 electrodes, and then you have basically, one of them grounded, one of them RF source, and you see this light. Why is this light coming in here? Pinkish light?
Because of argon gas.
Because of argon gas. Vaibhav, do you know etching before? Anybody can tell me why the light is coming?
Electronic transitions.
Very good. Satya Karthika. Sorry, I'm sorry, because my window doesn't show your full name. Satya Karthikeya. Okay, fine. Yeah, what electronic transitions are you talking about?
Sir, electrons at high energy possess different, maybe different colors like that.
Electrons have different colors. I thought only human beings have different colors. No, yeah, higher energy, when basically think of the Bohr's model, no? Whenever you have transitions from higher energy states to lower energy states, you have a photon emitted, right? So an electron is absorbed or removed, and then that essentially gives you photons. Okay, you can have sodium vapor lamp, which has these characteristic transmissions that give you the transitions which give you the yellow light. Okay, similarly, mercury lamp, you have whitish light, right? You have broad range of emissions. So oxygen will have a different transition. Oxygen plasma I can have fluorine plasma and so on. Essentially, they are in some kind of pinkish color. All right. So with that, if you have such a scenario, this is what you get, and you can use this to etch. Okay. Now, how do we make this happen? How do we create this low pressure? So a few things in this chamber are important. You have the gas inlet. You can have argon, carbon tetrafluoride, oxygen, and so on. It is not enough to have only gas coming in. You also have to have gas going out, right? You have the inlet, and then you have the pump, which is pumping out, right? And so by controlling the flow rates, as somebody mentioned, right? If you control the flow rates, you can quickly replace the gases or reactive species. Okay. If you have very large flow rate, then maybe, you don't have sufficient time to create even plasma. It might be difficult to sustain a plasma. So there is some flow rate you have to maintain, some pressure you have to maintain, and so on. Okay. And in addition, this RF is not really, it's not that straightforward. There has to be something called as a matching network, which essentially impedance matches and things like that. There are some tricks you have to play with this. There's an RF source, and then you high power RF source, and then you have this sort of a chamber. Okay. When you have this chamber, it is not enough to just have plasma. There's something else that happens. Okay. Because we have an electrode, which is, let's say this is a cathode and you have it at a low potential, electrons can quickly get accumulated. Wait, I'm sorry. Electric field is this way. So positive ions will come forward like this. So there is a small region where essentially the electrons will quickly go into the substrate and the positive ions are left on the top, right? They don't move as fast, we said, right? So there's a small region near the surface of the wafer, which we call as a sheath, wherein there's a strong electric field which is present. Okay, that's called as a sheath here. So the electric field is what is represented here. So think of just at the interface, right? Because your RF is causing the electrons to be ripped apart, and because they're very close to this, they quickly travel to this, and there is a small region where there is no plasma really, and then there is a voltage across that. Okay, and now this is very useful because since you have an electric field here, the positive ions actually get accelerated through this and hit the surface with a higher energy. Okay, so if you have this, you essentially, if you have a low pressure, you can have highly directional ions hitting the surface, and they also get more energy than typical, right? Because of this acceleration through the sheath, you'll have an accelerated ion energy, and then there is etching happening. Is that clear so far?
So why the negative ions going back, like there is a
Because
backward?
just to show you that there's an electric field, so it should go opposite direction. It cannot go in this direction. That's all it is. Okay.
Okay, sir.
Yeah.
Sir, to maintain the constant pressure, sir, by introduction of gases, it's still like introduction of gases affects the pressure of the chamber.
Does it?
I guess so, sir. So, like, my question is, should we gradually keep decreasing as we introduce the gas?
If you come here, I'll let you experiment with that. Okay, that's a practical thing that you have to do. Yeah, it's not like I'll flip on a switch and then I'll have the plasma. You have to, if you have very low pressure, you don't have sufficient ions to actually initiate a plasma as well, right? You will not get the glow. But if you have very high, again, you will not get a glow. So maybe initially the pressure is slightly higher. Instead of 20 millitorr, you start with 50 millitorr. And then once the plasma strikes, you try to lower the pressure. All right?
Got it, sir.
Yep. There are a lot more tricks you have to play. It happens to me. Some of our staff are also here on the call. Whenever they say, oh, plasma is not happening, I say, no. I mean, you have to, it's not that, you'll just click and then you won't have the plasma. You have to do some things to it. You have to understand what is happening. You play with the parameters, you will be able to do it.
Sir?
Yeah.
Sir, by using this method, can we etch complex things like cantilever bridges, or else, some kind of hanging structures where there is a small hole and underneath that it's carved?
Yeah. You don't need this also for that. Even cantilevers can be done with even wet etching, MEMS.
Wet etching, sir. But
wet etching. Yeah. Dry is better.
But if at all we are using, what will be the difference if we are using this and that? Will that be more?
Wet will have something called as stiction. So basically, when you try to have liquid evaporate, if you have wet etching, you will actually have the liquid in between the cantilever and let's say the substrate, right? And as it dries, it tries to make the cantilever collapse onto the surface. Okay. So there are some techniques called critical point drying and all that, which you have to use to make sure that carefully, without collapsing, you release these structures. But in dry etching, you don't have to suffer with all that. Make sense?
Sir,
but etch rate will still be less. Etch rate will be a problem, but yeah, it can be done. Sorry. Yeah.
Sir, what will be the difference in the shape? Will the shape differ in both the cases, or that's not that significant?
Shape will differ because it's more anisotropic. It depends on, see, if you want there's a problem here. If you want this is your cantilever and you want to etch it underneath in a dry etching system where you have anisotropic etching, how will you etch underneath? It won't work, right?
Yes, sir.
So you essentially have to make it operate under a isotropic or, isotropic mode, wherein you increase the pressure. Let's say you have some substrate like this and you have a cantilever, and you want to, let's say, remove silicon dioxide underneath it. So you have to increase the pressure so that the gas can go underneath and then create it. But the moment you increase pressure, how do you create a plasma and all that? A lot of issues will come. Something to be discussed. Okay? I cannot give you a simple answer for that. The color of plasma is also in different cases. I don't know. I have not honestly seen green plasma. Yeah. I've not seen green plasma. I have seen different shades of pink, yellowish kind of a thing. I've seen green. I have not seen. If you have to get green, probably you have to use something like strontium and things like that, right? I mean, I'm very poor in chemistry, so I'm not certain about that. You have to explain to me. Can you mention why the gap between the plasma and the material is formed? No, the idea is, this is slightly tricky subject. I mean, tricky. You have to, it takes you a bit of time. Okay. So if I'm not doing justice to it, you also look up on YouTube, you'll find some interesting videos which will explain this. Okay. In essence, what's happening is, there are a lot more animations which help you understand this better. So, but anyway, in essence, what's happening is, if you're very close to the surface, when you have this ionization happening, when your RF source is switching, these electrons do not need to travel. I mean, they are very light. They will travel very quickly, right? So what ends up happening is, in the small region, you have electrons which are completely, you don't have any more electrons here. Okay, they are completely taken out of the substrate. And so because of that, there is a positive charge that is there slightly far away. And this region where there is essentially no plasma, close to the surface. It can be a few, okay, I don't want to speculate. I actually have to check it up carefully. Maybe Rajshekhar or somebody can check it up and tell me this. Okay, but I assume that maybe less than a millimeter or something. All right. There will be a small distance wherein you have the positive ion and then electrode. So because of that, there is this electric field, this is called the sheath region. Sheath is essentially something which is covering, right? Think of this plasma. Around the plasma, you have a kind of a region without any plasma density. That's a sheath. Okay. And the voltage across this small region typically is like, 400, 500 volts, or even 300, 400 volts maybe. Right? So, and then because of that voltage, they'll get accelerated and then they'll hit the surface with high energy. Did I answer your question, Akshay?
Yes, sir. Thank you.
Okay. Adya had a question. How do you measure the strength of the plasma? Oh, very nice, Adya. How do you measure the strength of a plasma? Any guesses? Why do you guys not speak here? I mean, it's easier. Okay, anyway.
Based on the voltage discharge, we can calculate the thrust generated by the ions.
I don't know what that means.
I mean, the discharge voltage.
That is what you set, right? I can set my voltage, whatever, some 1 kilowatt I can apply here. Okay, power. That, yeah, if I make it, if it's brighter, I assume that it is stronger. Plasma, that's one answer, Adya. The other answer is, percentage of
ions and electrons.
Well, how will I know it real time?
Sir, can we monitor the temperature?
Lohit, temperature actually, if you go into it, I'll come to it a little later. The substrate is actually maintained at a temperature. We try to cool it with liquid helium. Not liquid helium, liquid nitrogen. Wait a minute. There is some kind of a cooling. Helium cooling will be there, not liquid, but helium cooling will be there. We try to maintain the substrate at the same temperature, because if temperature changes, substrate temperature changes, because you're bombarding it with a lot of ions, right? Of course, the temperature of substrate will change. And then because of that, the H rate will change. So we have a problem controlling the process. So we actually try to maintain the substrate at a fixed temperature. Okay. One of the ways to monitor the density of plasma is to use what is called as optical emission spectroscopy. You're seeing light, right? Put some of the light in a spectrometer. Look at the strength of the peaks. You can get the composition also to some extent, and you also get the strength of it. Yeah, the brightness, but brightness with some spectroscopic information at what wavelength you're having the brightness. Right? Sahiti, energy, question mark? I don't know. Yeah. Frequency, energy, frequency, lambda, wavelength. Come on, throw some more words at me. All right. Okay. Now the question is, yeah, optical intensity is good, but optical intensity as a function of wavelength. That is what is spectroscopy. Quasi-stat. Come on. Oh, Anand, good try. All right. Okay. So now the question is, there's a problem in this. Again, this is the simplest possible thing, and we call it capacitively coupled plasma. No guesses. No points for guessing that this is capacitor plates, 2 plates. You're applying a voltage, and then you're having this. Okay. The problem in this case is you have, if you want to increase the strength of the plasma, you are increasing, let's say, the input power. Instead of 1 kilowatt, I'll make it 2 kilowatt power source. Okay. Anish, just a moment, I'll come there. So you are creating a stronger plasma, but automatically the velocity with which they're striking the surface is also changing, and it's increasing, right? You're creating a stronger plasma, but then you have larger number of positive ions here, and then they will strike with a greater velocity. So you might actually damage. What happens if your velocity increases? Okay. Now, if I go back, I talked of selectivity, correct? What did I mean by selectivity?
Not damaging the mass and only etching the substrate.
Right. What happens to selectivity if my incident energy is very high?
The highly kinetic energy
It will reduce the
ions will
selectivity.
also damage.
Selectivity reduces. Very good. Selectivity reduces, right? Because high energy atoms don't care whether it is masked or a substrate, right? When you get angry, you don't care about anything. You become a Hulk. So we don't want Hulk, right? So you want control on that. Okay. So that is difficult to achieve in this kind of a capacitively coupled plasma, right? So for that, we use what is called as inductively coupled plasma. Okay. So what you do in this case is the machines that we have are ICP machines. Okay. We call it ICP RAE. ICP RAE is a combination of both. So what essentially is happening is, instead of a capacitive plates like this, you have a ICP source, we call it ICP generator. So essentially you have this coils, okay, and you essentially apply voltage, apply the RF power to it, and then you create a plasma. Similar concept, but essentially your ions will keep moving up and down, and then you rip them apart, and then you create a large density of ions. Okay, so you create this with one RF source, and then you also have a second RF source, which is basically applied between this and the substrate here. Okay, so you have two sources instead of one source. Okay, so one of them is ICP source, which is controlling the density of plasma. I'll independently increase the amplitude of it, the power applied ICP source, and then I'll create lots of plasma, and then I'll just make them come onto the substrate. Make sense? Right? With this voltage, if I apply less voltage, they'll come down with lower energy. All right. There is a question for all of you. Maybe I'll, you can even write to me if you figure out the answer. Okay. Why do you want inductively coupled? Why not capacitive in this direction? Why do you need to have a coil like this? Why can't you simply have a capacitor? Yeah, magnetic field. Yeah, I agree. Magnetic field, Rahul. But yeah, I mean, it needs to be a little bit more. Okay, I want to know why it is not a capacitive plate here. Charge buildup. Yeah, I think you need to look up a little bit more. All right. Yeah, there is this force is perpendicular to the magnetic field. Very good. So what? Soham.
Sir, so then we can direct the ions downwards or upwards, which side we want, depending upon the magnetic field.
First of all, I don't want the ions to go to the top. I want them to go down. But anyway, it's an RF source. They'll keep inverting. Why? Okay, I'll leave it. You come back. Okay. So yeah, I mean, the bullet points are there already. So RF source, this is for the problem of capacitive coupled plasma, that your RF source is controlling both of them. Your ion concentrations cannot be independently controlled, and then there is a power plasma generation and the sheath acceleration that's getting distributed there. But if you have an ICP source like this, you can actually do a low pressure. You don't really need high pressure, because you have independently a control on this, and then you can control the energy with which you bring down on this one. Okay. So these numbers, some typical numbers I have put here are, let's say, RF capacitively coupled, let's say, and ICP coupled. Forget the words HDP and all, high density plasma, but essentially the same thing. Okay. The idea is, you see the main parameters. What are the main parameters for an etching process? These are the ones. So you have the pressure, you have the density of plasma, you have the ion energy, and the ion density, whatever, electron temperature. I think these are okay. Anyway, the main point is, what is the pressure? If you have this ICP systems, you can actually get much more lower pressure. Why is low pressure important?
To reduce the mean free path.
Well, that is one question. What else? You're done? Yeah, 15 minutes. I told, 1 second, I'm sorry. So sorry, yeah. What are the other advantages? Improved directionality is very good. Yes. So if you want nanoscale structures, you need ICP. You can't do capacitively coupled plasma. All right. And density is more, of course. That is something we like it very much. All right. And then the other things, yeah, we will come there. All right. Next. Any questions so far? Are BTech guys, sir? No, nothing. Yeah. Anything else, guys? Any questions? HDP is high density plasma. Yeah.
Sir, why is the ionization rate decreasing? Okay. No.
Where is this? Ionization rate is lesser. More or less?
Yes, it is more.
Yeah. Shouldn't it be more, Ayush? Ayush from our ICMP?
Yes, sir.
Okay. All right. Yeah. It's more, right? Density is more. That's what we like. Low losses in power, less losses in power. What is it, Soumya? Soumyan, sorry. What is RF full form? Very nice. I have some experts in RF, I believe, there. Radio frequency. Is Anirudh here? Okay. All right. Anyway, let's move on. Yeah. Anything else? So why to use Soumya? I'm not going to answer that question for you. Sorry. You're going to answer that. You can send me an email. I'll see. Or you can. I want to know. Maybe you want to find out because I'll put a question on that in the exam. Guys, all right? Yeah. So, well, I don't want to go here.
So, like, we were using some matching networks also.
Yes.
Sir, why so?
I spent a semester telling you why matching is required. So, I'm not going to answer it here.
Yes.
Okay. Yeah. So, yeah, one more figure of merit that we have not discussed is basically anisotropy. Okay. There are various ways of giving it. Some books prefer this expression, some books others. So basically you have anisotropy factor AF, let's say, 1 minus horizontal etch rate by vertical etch rate. Okay. If you have isotropic etching, wait a minute. Yeah, when you have isotropic etching, what happens? The horizontal etch rate equal to vertical etch rate. So essentially, anisotropic factor is 0. There's no anisotropy. Okay, 0 horizontal etch and maximum vertical etch, you get anisotropy factor of 1. Okay, so this is one way of measuring anisotropy. So you essentially have, there's also sometimes what we call as a bias that happens. So, this is an interesting way of thinking about it. Okay, the idea is you are basically etching a film through a mask. So you're going to undercut, right? So why don't we make the mask slightly, the opening slightly smaller? Yeah. The question is, we understand that you have an isotropic process, there's a mask, there's going to be an undercut like this. Why can I not simply, let's say this distance was X, right? Can I not make it smaller, some X minus Y something? so that I can take care of the undercut also. Can I not simply do that instead of developing this complex etch process? What happens if I do that?
So the resolution might get affected, like the pattern's resolution. It might not be etched.
No, patterns will get etched. No, the problem would be, that is going to depend on the thickness of the film. So you don't have good process control. The moment you change the film thickness, you have to again redo the whole thing. So it becomes harder to control. Okay, that's. But instead, if you have, this is kind of self-explanatory, saying that, if you have more anisotropy, then you are able to etch down, not in the lateral direction. Critical dimensions, critical dimensions are harder to control. Yeah, that's there. Okay, so you have, the over etching is more in thick films than in thin films. Okay, so that's essentially the whole story. Now, again, this is something that I have discussed, but then I'm just going through with it. So you have basically some kind of a photoresist, and then you're trying to etch a film, and then there is an undercut, isotropic etching and anisotropic etching difference, and then there is sometimes mask erosion. This is an important part, right? You have a mask, and that mask also can get damaged. Sometimes that also has to be taken care of. Okay, so basically you define what is known as selectivity for a process. Okay, so what it means is you have some etch rate for the material and etch rate for the mask. So you want selectivity, we refer to it something like 5:1 or 10:1, right? What that means is you are etching the material 10 times faster than the mask. So you prefer high selectivity. Okay, so here, okay, if I look at this picture below, can you tell me what the selectivity is? Well, selectivity is not defined by you. If it doesn't react,
Y by X.
Who is that?
Y by X, sir.
Okay, Anand, yeah. So is that Y by X? Everybody agrees? You're etching the material by distance Y. The mask is getting eroded by distance X. So Y by X is your selectivity. Or Y is to X or whatever, Y by X. Right? So that's your selectivity. Very good. This we have already covered. So now this is the essential principles of dry etching. I'll take maybe 10 more minutes. I'll close. I mean, you guys have been good, so I'll not torture you more. But there are a lot of things that need to be done. Okay, so there are a lot of process control knobs. Well, I'm getting more responses. Okay, yeah. Let me stop sometime. Okay, just give me 5 minutes. So you can control various parameters, ICP power, RF power. You can get various things. So process optimization is a very complex job. Okay, so it's not that I'll simply put the sample in a machine and magic will happen. Machines are capable of magic, but the real magic happens in your mind. Okay, so you need to understand the processes and you need to figure out how to do this. For example, this is gallium nitride. I just found an image. I don't even have a proper reference for it. There's a PDF available online sometime. I found it. This is gallium nitride getting etched at different ICP powers and RF powers in ICP array machine. If you don't do the exact matching of balance of these two things, if you, for example, do it properly, then you get a very nice etching. This is gallium nitride remaining, and here gallium nitride is etched. Very nice, almost neat. But then suppose by chance, if you use low power ICP, but then more of RF, you get these pillars kind of thing that also come in. I think this also goes back to somebody mentioned redeposition, which I deliberately ignored when I saw that. Okay, somebody mentioned, I forgot. Okay, so if you have etching, right, you're also going to damage the mask. Sometimes what can happen is mask can get sputtered. I think by now you must have been introduced to the word sputtering, wherein your ions can come and damage the mask, and some of it can fall here, and then it can actually act as a micro mask. Okay, so you end up getting this kind of, that will be locally acting like a mask, and then you etch it around. So you end up getting some needles like this. That can happen. Okay. Yeah, don't. I mean, if you really show the, if you really see the scale of things that happen, the magic that happens, it's literally. I mean, I don't know. Your hair is going to stand up. The technology is so beautiful. Anyway, suppose if you don't do that and you have low power and then more of ICP, then you end up getting some pits like this, right? So there's always this balance. This is just with the RF power and the ICP power. You also have flow rates, the gas mixtures, right? I'll ask you one question. Okay, let me see if I can do this. This is something that I have done maybe about 15 years back. Okay, I was an initial beginning grad student. I was trying to get what we call as nano antennas. Okay, so it was simple enough, I thought. I mean, well, I was learning it. So I took a silicon wafer, coated some PR, rather E-beam lithography, did the pattern definitions, then did aluminum deposition, and then had this kind of small nano antennas, which are essentially aluminum. And then we are supposed to do RIE, okay, and etch down into silicon. The pink is silicon. After that, I'll remove the wet etching of aluminum, right? So I remove aluminum, I end up with kind of this antennas. Okay, these were supposed to be nano antennas. Okay, pay attention here. All right, everybody paying attention? So yeah, good. So when I say this, you might want to remember it. This is a very subtle or not so subtle hint. Okay, so I have these silicon nano antennas. And if I look at them, I of course had a periodic array of them. So these are sequence of antennas that I fabricated. And I get something like this, right? What is going wrong? I wanted to get nano antennas, but I ended up getting a bunch of ET, right? ET is, I don't know if your generation is familiar with that or not. There's an old movie ET in the 80s, I believe. Yeah. Now I don't even know whether you guys have seen the ET movie or not, but essentially these things, some alien creatures with the head and all that. What is wrong here? Small pillars. Yes, of course, they are small pillars. Yeah, why? What is wrong?
Etching looks like it was isotropic. So because of that,
what should I do, Rahul, for that?
There is like a bulkhead.
Yeah, bulkhead. Yeah. So in the top, there is something that is protecting, but underneath there is more isotropic etching. That's why you see that these things are almost standing on a very thin. So the waist region is kind of small or something like that, you can say, right? There is some undercut, essentially. Why is that happening? What would you do, Raghava? What would you do to solve this?
Might be reduce the chamber pressure and increase the gas flow rate.
Well, gas flow rate. If you is it possible to increase the gas? First answer I like. Okay, chamber pressure. I will reduce the chamber pressure. So I got here 7 pascals. Translate 7.5. That's about 50 millitorr. Let's say from 50 millitorr, I'll bring it down to 20 millitorr. Okay, very good. Should I increase the gas flow rate or not?
Yes, sir.
No,
sir. RF biasing. Maybe by increasing RF biasing, we can.
If you do RF biasing, you will make it. Well, you'll make it more vertical. That is true, but you'll also end up eroding mask. So unfortunately, in my process, I had aluminum. Aluminum is not a very strong material. It can easily get, that's why you see here, this kind of in between here, there is a lot of speckle or dust kind of a thing, right? These basically aluminum has got sputtered and then that is micro masking. Okay. So not a very simple thing to increase RF power. Is Rajshekhar here? Not Rajshekhar. Who else is here? Anup is here?
Yes, sir.
Good. All of you are listening, right?
Yes, sir.
You understand? I mean, it's important for you guys to get this.
Yes, sir.
Okay. If you have aluminum deposited here, if you simply increase the ICP power, right, or not ICP, RF power, it will simply sputter the aluminum and then it will cause micro masking. It won't work. What else can be done? Flow rate, Raghava.
Sir.
What do you say? Flow rate increase or decrease?
If we increase the flow rate, then might be the pressure would also increase consequently.
Very good. Yeah, flow rate. It is difficult to maintain low pressures and high flow rates. If you if your chamber pressure is high, it's much more easier. If your chamber pressure is very low, your pump has, thanks Anup, hi. You can switch on the movie video. All right. So your chamber pressure is, Anup, you have to switch off. I'm sorry. Okay. Yeah. So your chamber pressure is low. It's very hard to have a, high flow rate. Your flow rate has to reduce. From 30 SCCM, you have to make it 10 SCCM or something like that. If you increase the flow rate, you're going to not be able to maintain the pressure. All right. That's one. What else? Very good. Low pressure with more time, yes. Reducing RF power, very good. That's essentially the solution. Okay. Do I have it? See, I'm the magician, and many of you guess the same thing, right? The first one, the second one. Looks more realistic, isn't it? Of course, I still have these top heads. That's a story for another day and time. All right. Makes sense? Just going from 7 Pascal to 2 Pascal. I'm getting more straight side walls. Okay. I think our staff also need to see this. Anyway, all right. Okay, good. Next question. Anything else? Well, I don't want to. Somebody mentioned DRIE. Essentially, okay, we have 5 more minutes. It's sometimes difficult to get very high aspect ratio structures. So what we end up doing is we combine etching and passivation steps. All right. So basically what you have is you have the etching step. If you try to etch very deep, you also invariably start etching under the mask. So what you do is you keep cycling. You etch and then you deposit some polymer on the side. Again etch. You deposit polymer on the side. So you end up getting not a very straight side wall. There is some roughness, but you can develop what is called as a deep RIE process, wherein you combine this etch step and a passivation step, and you can get very, very high aspect ratio structures. Okay. And if you look at it later on, I'm running out of time, but DRIE can be explained in the, DRIE was explained by whom? By Prempal. Okay, very good. All right. Then essentially, yeah. So you have you basically have in the passivation step, you have basically C4F8. In the etching step, you have SF6, and you control appropriately the powers and so on. You etch silicon or don't etch silicon. That's all. Okay. So you have a passivating gas C4F8. So with that, you will be able to etch deep aspect ratio structures. There is also a lot of complications. Again, I should stop, but this is micro masking, which we also call as grass or something like that. So essentially your mask is getting sputtered. Can we remove what? I'm sorry. Just 1 second. Shilpa. Sorry. Can we remove the bulk part totally in practical? What is bulk? Well, tricky. That's why I didn't answer the question. Okay. We'll talk. If you're here, we'll talk. There's also other issues. Something is called, the etch rate is not going to be uniform still. Suppose you have structures which are small gaps and large gaps, you will still have some different aspect ratios. Depending on the aspect ratio, your etch depth can be different. Again, something that has to be controlled. It kind of is obvious that your gases are going in faster, and also, so it's etching faster. Somewhere else it is etching slower, right? So this is again some unwanted effects which we have to, depending on the density of features. Think of your millions of transistors. You have to etch many, many holes like this across the wafer. So all of them have to be uniform. So there are a lot of things that need to be controlled for that. And then you also have, if you have openings in one small area, isolated openings versus a periodic opening here, because the gases are more distributed here, the etch rate, effective etch rate here is going to be lower than etch rate here. Okay. So these are all again effects that can happen that need to be considered and analyzed. And summary, yeah, this is something else. So yeah, it's not enough to have this. You want to go here, right? This is so beautiful that, Oxford is selling machines based on these kind of images, right? So yeah, that's about what I want to tell you. I have maybe 3-4 minutes of questions. And we will talk tomorrow again. Anyway, we'll talk more general things. Already I think I'm probably hitting you with up to the saturation point. How many of you are saturated now? Or you can take punishment for one more day. Parashuraman, yes.
No, sir, by mistake.
Oh, you saturated. I thought you can take more punishment. Last time you came and then one more time you're doing, no? I thought you can take more punishment.
Actually, I just want to revise everything. I'm doing a project right now.
Where?
In IIC.
Oh, very good. Very nice. What is that? LMOA. Arey yaar, come on, I'm old man. What is LMAO? Huh?
Sir,
Aditya, what is LMAO? Laughing. Hey, Nishant, do I know you? Your name seems familiar. Anyway. I see. Okay, fine. Good. All right. Chalo. Anything else?
sir, can I?
Yeah. Yeah, please. Go ahead.
Like most of the structures given in the examples and the ones you created were like vertical.
Mm-hmm.
So what if I want to create a V-type structure? Is dry etching both?
V-type structure with dry etching, I don't know how to do that. I don't know how to do a smooth V-type structure. I can do multiple steps, gradually reducing my etch rate. Okay, but it's going to be much more tricky to do that. Yep.
So wet etching is the best possible method.
Yeah, wet etching. That's what. Yeah, in that kind of specific example, wet etching is better probably. You're forgetting day one. It's all right. You're going to come here. If you come here, you're going to get again 3 weeks of revision. Yeah. Srimathan. In ICP, we accelerate ions in those helical. No, I don't want to talk ICP. You're going to tell me that. It's an abbreviation. Oh, I see. Now I understand. That's why nobody is giving the abbreviation. All right. I'm too slow, right? It's like my antennas are not sparking. Okay, anyway. Yeah. So earlier I said that purple color is due to argon. What I meant to say was it is because of combination of blue and red. Well, I don't know. Yeah. Yeah. All right. So didn't you try reducing RF that time? I knew RF has to be small, so RF was 20 watts. If I go any lower than that, it's as good as not having. I mean, I didn't go lower than this. Generally, you do RF of 100 watts. So 20 watts already was quite low. So I didn't know what else to do. If you put 100 watts, everything, all the mask will go. There's nothing you can do for that. Yeah. All right, guys. I think I'm sorry I have to stop here. It was nice interacting with you. Tomorrow we'll have a more casual session, more storytelling. Okay?
Sir?
Yeah.
Sir, in the quiz, what kind of questions could we expect, sir? Because till now we have been learning a lot of theory things which were taught kind of fast.
Yes. You try to get a high. See, of course, I'm not going to ask you intricate details of, how do you do this, right? Are you having a high level understanding of the process, right? And the questions, at least, see, this is one person is not going to set questions. People are going to have, a lot of faculty will have their questions. So everybody will have their own ways of dealing with it. But in general, I would say that if you kind of made sense, if it kind of made sense across the lectures, right? At least the high level, big picture, if you're able to get it, you will be able to think and understand. Don't think that you have to answer all the questions. Last time I did a very devious thing. And then the answer was, there was some very, anyway, I don't want to go into what I did. If you don't try to answer everything, try to answer sincerely. Whatever you are confident about, you will do fine. If you try, there are 50, 60 questions. If you answer all of them, then you will suffer. Okay. Try to be a little bit more cautious. Try to understand. Nobody's expecting you to be an expert in VLSI fabrication. Okay. And our intent is definitely not to conduct the JEE examination. Okay. So, yeah. Don't, yeah, don't take too much of pressure on that, but try to get a high level picture. Yeah. And I'll also, this time, I think I have to discuss with our team also, but I think we'll give you a time, a few more, some days. We'll give you some time. I think Abhishek will announce it someday. He has to discuss with other faculty and we'll announce a date for the exam. We'll give you some time to prepare. Yeah. All right. We want recordings. Do dharna. I am not responsible for it. How many other times you do, it doesn't help. We are trying to do, but we are also, see, Abhishek also is constrained by so many things. All right. Time is most needed. Very good. Thank you, guys. I have to bye.
Thank you, sir.
Bye. Bye, Abhishek. You can stop, I think, recording. Yeah. Bye.
Yes, sir.
Thank you, sir.
Recording for day 1, 2, and 3 already uploaded. You can check your WhatsApp.
Sir, when is the next session, sir?
Recording already uploaded.
Sir, has the lecture slides also been updated on the drive?
Lecture slide yesterday I shared in the folder. In that folder you will get lecture slide. But professor is uploading one by one. It may take 1 day more. You will get both. Don't worry.
Okay, thank you.
Sir, when is the next session, sir? 4 o'clock.
4 o'clock.
Okay, sir.
Sir, when we can expect the examination?
I don't know regarding that.
Are you sure? Not this week?
That's you may write an email. Okay. Thank you. Please be available at 4 p.m.
Sir.
Yes, tell me.
Sir, round 2 will start on 16th only, right?
No, it is not decided yet.
Oh, it's tentative.
Tentative. Maybe
Okay.
it will be postponed another 1 month maybe. I'm not sure. Because there's some issue. That's why maybe we will postpone 1 month.
Okay, sir. Thank you, sir.
But sir, by that time, I think a lot of colleges will reopen.
When all the colleges are reopening?
Sir, for NIT Trichy, I think it's reopening on 7th college. 7th July, sorry.
7th July. Okay.
So mostly it will be in the first and second weeks of July only.
Understood.
Yes, sir.
We are trying to contact as soon as possible.
Excuse me, sir.
Yes.
Sir, so my name is Arushi, and sir, today do we have an exam at 6?
I'm not
That
sure.
demo exam, not the final one, demo.
I will ask Hari. Hold 1 minute.
Sir, do we have any assessments today?
I guess there are demo examination.
It is
Okay,
not
sir. Got it.
mandatory, sir.
Hari, could you please online?
Hello.
So I am starting one poll. Please vote. How many of you wants online mock exam today?
Sir, mock exam means it will be simply 10 minutes exam or like a full-fledged?
10 minutes exam. Just for your checking, everything is going fine or not. It will be not counted.
Okay, sir.
Please vote, everybody.
Yesterday, if we did, then no problem, no, sir.
Hello.
Yes, tell me.
Hello, sir. I have sent a message to you over WhatsApp. Can you check it?
So I received many messages, unable to check all the messages.
Okay, sir. Can you tell me the support mail ID? I will send you my query there.
You want to?
The support mail ID. I will send you my query over there.
Okay. So your phone number is last is 266.
Yes, sir. Correct. 266.
So phase 2 is not flexible dates. Okay, if we are still not decided, it is not decided yet when it will be happen. Okay. So whenever
Maybe it can go to July.
Yes, high chance.
Okay, sir. One more query is there, sir. In the FAQ section of the NanoX website, it is mentioned that if someone qualified for phase 2, he will not be able to apply for the next cohort. Is that so?
I guess yes. There will be phase 1, phase 2 will be offline session here, and phase maybe yes.
No. If someone qualifies for phase 2 and will not be able to attend the offline session, so he can apply for the next cohort or not?
Better tomorrow you can ask to the faculties. Okay, there is a feedback session tomorrow.
Okay.
From 4 to 5:30. Okay, tomorrow.
Okay, sir.
You can ask the specific question there. It will be helpful.
So actually, exams are going on for my section.
I checked your messages.
Uh,
Understood totally. Please ask there.
Okay, sir. Okay, thank you, sir.
No, we don't conduct everyday exam. So this is a mock test. So tomorrow we don't have any exam. Yes, day 1 afternoon session is not uploaded. I am already requested professor to upload it. Please wait for some time. I know that.